So as we've been going along with these chemical reactions, some things that I've been alluding to are the fact that some things are actually aqueous when they are reactants in a reaction. And that has to do with a topic called solubility. And so this particular VodCast is going to cover this issue of substances being soluble. Okay? So what we're going to look at here is what's called the solubility of salts. Now, one of the things you need to understand is ionically bonded substances, which are salts, and we've talked about that many times, dissolve in water because water is a polar molecule. Okay? And we'll deal with that issue in a little bit. Okay, now, not all salts dissolve. Okay? So one of the things that we have to talk about is the term solubility. And when we talk about solubility, it is the ability of a salt to dissolve. That's kind of the textbooky definition of that. And solubility deals with everyday things. When you go and you put something into water and make it dissolve, it's an everyday issue. So it's something that we should be aware of. Okay? And a couple terms that go along with this are the term soluble. And something that is soluble simply means it can dissolve. So a salt that's soluble is something that can dissolve. If a salt is insoluble, that means it cannot dissolve. Okay? So those are kind of some important terms that you should make sure you record in your notes. Solubility, soluble, and insoluble. Now, if a salt does not dissolve, okay, in a reaction, okay, it will form a precipitate. And a precipitate was one of our indicators of a chemical reaction. And a precipitate is a solid that will fall out of the solution. That's a precipitate. Okay? And you've seen precipitates. I've shown you examples of them. And you're going to see a lot of precipitates in the next lab that you do. Now, going back to the issue of water for a second, okay? What I want you to do is draw the electron dot structure of water. Okay? So take a moment in your notes and draw the dot structure of water. And you should be drawing oxygen with its 6 dots, and then hydrogen attaching onto it. Okay, now, as you look at the electron dot structure of water, okay, is water polar or nonpolar? And going back to our chapter on molecular geometry, you should be able to look at this and tell me the fact that I have unshared pairs of electrons makes this water polar. Okay, and this side of our water molecule is negative, and this side of our water molecule is less negative, which makes it positive. Okay, so water is a polar molecule based on its shape, and you should also be able to tell me what its molecular shape is. And so hopefully you can remember that that's bent. Okay, now, if you look at a salt, and we'll look at a simple salt like NaCl. One of the reasons why water can dissolve salt is because NaCl has a positive and negative charge to it. And because water has a positive and negative charge, what a water molecule can do is this water molecule can literally come in here, and the negative side of the water molecule can actually attract itself to the positive side of the sodium chloride, and it can literally take that sodium chloride and rip it off. Okay, so that sodium chloride can become ripped off, and I'm going to show you an example of that. Okay, so as we take and we dissolve salt, so this is just putting some NaCl into water. Okay, the water acts as a solvent, and molecules can dissolve. So now we're going to look at an exploded view of this. Here you see the water molecules coming in. The negative side of the water molecules rip off the positive sodium, and the positive side of the water molecules rip off the negative chlorine. And that frees up more molecules that can come in, and where water can come in and rip those apart, okay? And then what happens is, once those get ripped off, more water molecules surround it, and that's why this remains dissolved, because those water molecules can no longer interact with each other because they're literally surrounded by, oh, I think I said water molecules. Those sodium and chloride molecule atoms can no longer interact with each other because they are surrounded by water molecules, okay? Here's another example that I want to show you, okay? So if you watch this, okay, you can see water molecules going in and ripping off sodium atoms and chlorine atoms from this big solution. We're going to go look at a close-up view here. Okay, so you see the water molecule going in there and literally ripping off, okay, the negative chloride ion. And up here in this picture, you see that that negative chlorine ion is surrounded by the water molecules. Okay, so one more time, goes in, rips it off, okay, and it's surrounded. Okay, if we look at the other part of this, okay, here's the negative side of the water molecule ripping off the positive chlorine, the positive sodium atom. Okay, play that again. Going in, negative side rips off the positive. Okay, and then what happens in the solution then is these are all surrounded by these water molecules and they no longer interact with each other. Okay? So that's kind of what's happening when every single salt dissolves. Okay? Most of the examples on the internet involve sodium chloride. Okay? But you have to realize that this happens with every salt. Okay? So, the process happens for all soluble salts. So here I have silver nitrate. Okay? And what happens with this silver nitrate is, hopefully you remember that silver is a positive ion, and nitrate right here, okay, is a negative ion. Okay? So when this splits apart, okay, it's going to split apart, and it's going to break the positive ion of silver off and the negative ion of the nitrate off. And those are the two things that are going to split apart, and now they're going to have their charges with them. One thing to remember in this process is polyatomic ions stay together. Polyatomic ions stay together. Okay? So now, what we're going to do with this is we're going to write an equation to show these ions in solution. It's called an ionic equation. This is not really a reaction, so it's not one of our 5 types of reactions that we're going to. Okay? It's just an equation that's going to show the ions in solution. And the way we show this is this AgNO3, okay, is going to break apart, and it's going to break apart into its silver ions and its nitrate ions. So all we do is we take this up here, okay, and we put it down here, and we take this and we put it down there, because that silver nitrate broke apart and formed those 2 ions. And the one thing with this ionic equation is you must include charges. Of the ions. These charges right here absolutely positively must be included, and I put this example on here on purpose. If it's a +1 charge, okay, you can put plus or +1. If it's a minus charge, you can put minus or -1. It doesn't really matter, okay? But it does matter that you include the charges. So let's look at another process, or another one, okay? calcium chloride here. How do you suppose that would break apart? Okay, well, first of all, it's going to break apart into the positive and negative ions. Okay, so a calcium is going to break apart here, and so is a chlorine. But how many chlorines do you have? Okay, with this 2 right here, that means that there's actually 2 chlorines that are going to break off of that compound. Okay, this calcium is going to be a +2 charge. Each one of these chlorines is going to be a -1 charge when they break apart. So what we do when we write this ionic equation is I have 1 calcium and I have 2 chlorines that break apart. So this particular ionic equation is written like this: Ca2 plus 2 Cl minuses. And that all goes back to the fact that we have to have a balanced equation. Now, the thing that comes up many, many times in this process is, ooh, chlorine, that's a diatomic. How come I don't write Cl2? Well, in this particular case, because chlorine is an ion, then it's not considered diatomic. So ions are not written as diatomics. Okay? So in this particular case, we will not write chlorine as a diatomic because it's dissolved. Okay, let's look at another example. Oh, wait, before I do that. If I had 2 molecules of calcium chloride dissolved, okay, so I put a 2 in front of here, how many calciums would I have? And because I have 2, I would have 2 calciums come out of this. How many chlorines do you think would come out? And hopefully you said 4 chlorines would come out. Okay? Because that 2, as we learned in our balancing equations, that 2 goes to everything that's behind it. Okay? So this particular equation, if I were to write this, would be 2Ca2 plus 4 Cl minus. Okay? Well, what if I had 24 calcium chlorides? Okay, how many calciums would I get? And hopefully you would say 24 calciums, which is 24. And how many chlorides would I get? And hopefully you would say 4 dozen, which is 48. And hopefully you understand where I'm going with this. Well, what if I have 1 mole of calcium chloride? Okay, if I have 1 mole, that means I have 6.022 times 10 to the 23rd molecules. And remember, we're just going to use the general word molecules, even though this is really a formula unit. Okay, and so because of the way it breaks up, I would have 1 mole of calcium ions. Okay, 6.022 times 10 to the 23rd. And how many chloride ions would I have? I would have 2 moles of the chloride ions. 2 times 6.022, which would give me that many. And the whole point of that is we deal in chemical reactions in terms of moles. We don't actually deal in terms of atoms. Okay? Now let's look at another example. How do you suppose K2SO4 would break apart? Okay, first of all, it should break apart right there at the K and the SO4, because the K is the metal and SO4 is a polyatomic ion. Okay? And how many potassiums will you get? Okay, I'm going to get 2 potassiums, ions. How many sulfate ions? And I'm going to get 1 sulfate ion. So how would I write the ionic equation for this? Okay, hopefully you are writing it as this then. Okay, K2SO4 gives me 2K plus ions plus SO4 2 minus. Okay? Now, let's look at a fun polyatomic ion here. Fun equation. Okay, this would be ammonium phosphate. How would this break apart? And hopefully you would see that the two polyatomic ions would break apart. But how many ammoniums are you going to get out of this? And hopefully you see, because of this little 3 down here, you're going to get 1, 2, 3 ammoniums, all that have a plus charge. And then I'm going to get 1 phosphate, which was a minus 3 charge. So how would I write that as an ionic equation? And hopefully that's what you're writing. 3NH4 plus PO4 3 minus. Okay? So hopefully you're getting an idea of how to write these ionic equations. Now, let's do this one. Okay, I kind of set you up, okay, because this one does not dissolve in water. It's actually insoluble. Okay, so how would you know that? How do I know something dissolves and something does not dissolve? Okay, well, what you have to do is you need to find this chart. In your packet, you have a chart called solubility rules. Okay, this is a chart you actually need to learn how to use. Okay, and in this chart, okay, it gives you some general guidelines as far as what's soluble and what's not soluble. If you learn and memorize rule number 1, okay, that will help you about 80 to 90% of the time with what's soluble and what's not soluble. Okay? Now, soluble, at the top of this, okay, what I want you to write is soluble dissolves. Okay, go ahead and write that at the top of this sheet. Insoluble does not dissolve. Because sometimes we get confused with what soluble and insoluble does not mean, what they mean. Okay? Now, going back to this first rule. If you learn this first rule, this will help you quite a bit. Okay? And the first rule is all group 1 elements are always soluble. And so are salts of ammonium. But if you learn that all group 1 elements, no matter what they're combined with, they're always soluble, that will actually help you out quite a bit. But there's other ones that you can look at as well, okay? This 2 has a whole bunch of solubility rules, okay? And it kind of talks about the halogens, okay? So all chlorides are soluble except silver chloride, mercury chloride, and lead chloride, which are not soluble. All bromides are soluble except silver, mercury, and lead. All iodides are soluble except silver, mercury, and lead. Okay, so there you go. There's another rule where pretty much every halogen is going to be soluble unless it's with silver, mercury, or lead. Then it's not going to be soluble. Okay, so if you just remember silver, mercury, and lead are bad elements for solubility, okay, then you'll have a good idea of how to use this rule. Then these rules start getting real specific, okay? Then we're going to start talking about polyatomic ions. In rule number 3 here, we talk about chlorates, nitrates, and acetates are always soluble. In rule number 4, we talk about sulfates. Sulfates are soluble except when it's calcium, strontium, barium, okay, and those. Okay, phosphates. Phosphates, carbonates are insoluble except when they're within ammonia and group 1 elements. Okay, metal oxides are insoluble except with group 1 elements and compounds. Metallic hydroxides are insoluble except with group 1 elements. And actually it's group 2 elements from calcium down. And then all sulfides are insoluble except within group 1 and group 2 elements. Okay, so this is just a sheet that it's new to you now, but as you use it on the worksheet, you'll become familiar with these and you'll learn how to use the solubility rules. And it just becomes a matter of practice. Okay, so we're going to look at what salts are soluble here and which are not. Okay, so going through this list, I have cobalt nitrate. Okay, if you remember the list, we did not talk about cobalt at all, but we did talk about nitrates. So you have to pick out what's in your list, what's not in your list. Back in my list, okay, I had a rule about nitrates. Okay, here it is. All nitrates are soluble. Okay, so going back here then, this is soluble. And once I know it's soluble, then I can write the ionic equation for it. So once I know it's soluble, this will break up. And it'll be cobalt 2 plus 2 NO3 minus. Okay? Now, mercury chloride, soluble or insoluble? Go back to your chart. Okay? And I have a whole bunch of writing on this chart, so I'm going to get rid of a bunch of it here. Okay? You go to chlorides. Okay? Because that's a chloride. So in that chloride, that rule is right here. All chlorides are soluble except, oh, there it is. Mercury chloride is insoluble. Okay? So this is insoluble. Okay? What I want you to do is go down this list, and I want you to pick out what is soluble and what is not soluble. And if they are soluble, write the ionic equation. So, if soluble, write the ionic equation. Okay, so I'm just going to give you the answers now. Sodium sulfate right here, sodium sulfate, because sodium is a group 1 element, this is soluble, so you would write the ionic equation 2 Na plus SO4 2 minus. Okay? Barium sulfate, not soluble. Okay? Lithium chromate, lithium, group 1 element, therefore it's got to be soluble. So this is going to be 2 Li plus CrO4 minus. Copper chromate, okay, insoluble, not soluble. Okay, and I probably should use the term insoluble, so you get used to that. Okay? Cesium hydroxide. Oh, group 1 element, soluble. There's the ionic equation. Copper hydroxide, insoluble. Silver chromate, silver carbonate is insoluble. And the last one, silver bromide, insoluble. So now you have a worksheet that you should be able to complete on solubility.